Alright, in our last video we went through the top half of this worksheet where we did some cost minimization problems. Here, since we're assuming that we can change the amount of labor and capital, these are long-run cost minimization problems. We'll do short-run in just a minute here. So we looked at the least cost combination of inputs if labor costs $5 per worker and capital costs $20 per unit. And we found there we would use 44.3 workers, 22.15 units of capital in order to produce 1,000 units of output as cheaply as possible, and that our average total cost, our cost per unit, was about 66 or 67 cents each. And then we saw what would happen if we had to pay our workers more, ceteris paribus. Still producing 1,000 units, what would happen to the optimal combination of inputs, and what would happen to our average total cost? We saw that we would substitute away from using labor and toward using more capital, as illustrated by moving from the red point to the green point here, and we would instead use about 28 workers and 28 machines there. The optimal ratio of capital and labor is dictated by these equations here. In the first problem, where the wage was $5 and capital was $20, this equation says we would use half as many machines as workers. But when the cost of each worker or each worker hour increases, this equation, where we're looking at the slope of an isoquant equal to the slope of an isocost, simplifies into saying we should use more capital in relation to labor. Use the same amount in this case, instead of half as much as in the first problem we did. Even though we're switching away from using labor, our average total cost went up from about 66 or 67 cents per unit to almost 84 cents per unit here. The next problem we want to do here is look at the expansion path. What happens to the optimal combination of inputs as we expand our output or contract our output? Try to see what that relationship looks like. So over here, let's keep the wage $10 and the cost of capital $20, and let's find the cheapest way to make 400 units and 1,400 units. And if we connect those optimal solutions together, then we'll have what we call the expansion path. It's just a line that connects the cost minimizing input combinations so we can visualize what that looks like. So let's look at the problem we did last time and see which pieces we'll need to solve a couple of more of these problems. And I'm going to show you 3 ways that you can think about deriving an expansion path here. This equation is going to be the same since the price of labor is still 10, the price of capital is still 20, and the marginal rate of technical substitution equation isn't going to change since the production function hasn't changed. We're going to be able to pull this part, K equals L, as one of our equations we're going to need. And this equation, where we set the output level that we're looking for equal to the production function, that's going to be the same except we're going to change the output level here. So let's grab those pieces and set them up over here. So as you see, when we go to set up these two problems, everything's going to be the same except in one case we're plugging in 400 for Q and in the other 1,400 for Q. And we could solve as many of these problems as we want, just plugging in K equals L into this equation, and then simplifying and solving for one of the two variables, either L or K, and then we know that L is going to be the same thing as K, no matter what we do here, as long as these prices remain the same. So let's go ahead and start simplifying this to see what is going to happen. No matter which problem we're working on, we're going to want to divide by 50, right? And that 50 on the right-hand side will cancel out. And then we're going to want to plug in K equals L. So let's erase the K and just call that L. And we're going to be collecting the L's to get L to the 0.9. And so we're going to have 400 over 50 equals L to the 0.9. And then what are we going to be doing to solve this? Raising both sides to the 1 over 0.9 power, which is 1.11111. Now, I left the 400 over 50 here intact instead of simplifying it so that we can see what's going on here. Instead of solving lots and lots of separate problems with separate Q's, what might be a better strategy in this case is to just leave this number a variable, Q, and then solve it for L, and then we can plug in any quantity we want and find out how many workers we need, which is going to be the same as the number of units of capital in this case, right? So if we wanted to do that, we just erase the 400, say, okay, for any quantity we can do this, and let's solve this for L and see what happens. So if we raise both sides to the 1 over 0.9 power, we'll have L equals Q to the 1 over 0.9, which is 1.111111. Divide that by 50 to the 1.11111. 50 to the 1.11111, about 77.22. So what this lets us do is not have to repetitively solve these problems. If we had to do a lot of them, we can just plug in Q, whatever Q we want. So let's use this and see what we get. So let's plug in a Q of 400. You do the same to get practice. So here when I plug in 400 for Q, I'm getting that L equals just above 10. 10.08 or so. And then what if we plug in 1400 there? And we know that K is going to equal L, right? So now let's plug in 1400. And here I'm getting K equals L equals 40.54 roughly. So that's just a little quicker way to do this. So method number 1, just solve these problems individually. Method number 2, just solve this for L and use the fact that we know L equals K, and as long as we solve for L, then we have a solution for K. Now if L equals K wasn't one of these equations, so if K equaled 2L, we'd multiply this number by 2 to get K. If it was a half, we'd multiply it by half and we'd use 5 machines, right? So that's method number 2. I'll tell you about method number 3 in a second. Let's go ahead and plot these solutions. For producing 400, the isoquant for 400 is gray. So that's this one running right through here. And our optimal solution, given our current prices, was right here. And when we were producing 1,400 units, 1,400 units is going to be, it looks like a black isoquant here. Okay, so that looks like this one running through here. And again, our optimal solution was about 40 units of each. Now, if we connect these with a straight line, going from the origin in this case, because we know that if we're producing no units of output, the cheapest way to do it would be to use 0 workers and 0 units of capital, right? So we can draw this arrow, this expansion path coming out of the origin. And this brings us to method number 3. If you want to visualize the optimal combinations of capital and labor as you expand output, then in this case, with a Cobb-Douglas, it's just going to be a straight line. And what's the equation of that straight line? It's just K equals L. That same equation that we simplified up here for our equation 1. Again, this equation tells us how K and L are related to each other at the point where the slope of the isoquant equals the slope of the isocost. And since it's a linear relationship, when we're solving these Cobb-Douglas problems, the expansion path is just going to be a straight line coming out of the origin for Cobb-Douglas production functions. Now, there are other possibilities, of course. One thing you might see in your textbook as you're looking through it is there is an interesting idea about asking the question, in the long run, as we expand output, are we using more capital and more labor? And in this case, we definitely are. In that case, we would call both capital and labor normal inputs. This idea is related to the idea of a normal good. A normal input is one where as you expand your output, you're going to use more of that input. An input whose cost minimizing quantity increases as the firm produces more output. Now, there is a possibility where as you increase output, the cheapest way to do things might be to completely move away, or more completely move away from using people altogether, and maybe fully automate your factory, where you only need 2 or 3 people to run a very large factory. In that case, if what we saw was as we expanded output, we might imagine an expansion path that looks like this. Maybe beyond some output level, we should use less and less and less and less labor and just solely substitute labor for machines. This backward bending or negatively sloped part here would indicate that at least in this region of production, labor is an inferior input. It's very similar to the idea of an inferior good. Remember, an inferior good, when we're talking about consumption, is if your income goes up and you buy less of something like ramen noodles, that's an inferior good. An inferior input, similar kind of idea. If my total cost goes up and I'm producing more units, if I use less of an input, that's an inferior input. This is not going to happen with a Cobb-Douglas production function. Both inputs are always going to be normal because as we expand output with a Cobb-Douglas production function, we're always going to be using more of both labor and capital. So everything we've talked about so far is looking at long-run planning. I can adjust all my inputs. We're only talking about 2, but we could generalize this to 3 or 10 or 100 different inputs. Let's look at the short run. So the short run, again, is a short enough period of time to where at least one input is fixed. You can't change it. Personally, when I think about the long run, I think about today. That just crystallizes my thinking. Okay, what are the kinds of things I can do today? That's not really technically the definition, right? The short run is just a short enough time to where at least one input is fixed. But if we just think about today as an example, then you know today you could use more workers or less workers, but you probably can't expand your factory or make your factory smaller. So in the short run, we're going to assume that our variable costs are things like labor and materials. We'll just use labor as a stand-in for that. And our fixed costs are going to be capital. We can't change the amount of machines or the size of the factory today. So here is our problem. We have to tell you how many machines we have because that's not a variable. It's fixed. So previously, we decided to build a plant with 20 machines in it. That's what we've got. So K equals 20. It's not a variable. Today we need to produce 1,000 units of output. How do we do it? How much is it going to cost, and what's the per unit cost, the average total cost? Let's look at this problem graphically first. Graphically, here's the way I like to think about this. K equals 20. So K is over here on the y-axis, of course. And we're told that K equals 20. So let's draw a line at K equals 20. We have 20 machines, and there's nothing we can do about that today. We're stuck with them. So the question really becomes, if we're going to produce 1,000 units of output, and that's this green isoquant here, this one running right through here. If we're going to produce 1,000 units of output, how many workers do we need? Well, we just need to look along this isoquant where we're producing 1,000 units and go down here to the point where we have 20 machines and find out how many workers that is. How many workers do we need to produce 1,000 units of output? And that's going to be right around here. So looking at our graph, it appears that that would be 53 or 54 workers perhaps. Let's do the math and solve to see what we actually get. So instead of having 2 equations now and 2 unknowns, we only really need 1 equation because there's only really 1 unknown. And that 1 equation, we need 1,000 units of output, and that's equal to 50 times L to the 0.3 times k, k is not a variable, raised to the 0.6. All we need to do is solve this equation for L, and we have our answer. Pause the video and try it, and make sure that you get something in the neighborhood of 53, 54, 55. Alright, so to solve this, we're going to divide both sides by 50, leaving 20 on the left-hand side here. And then we need to figure out what 20 to the 0.6 is. Divide both sides by that. And when I divide 20 by 20 to the 0.6 power, I'm getting 3.32, leaving L to the 0.3 on the left-hand side. Then we need to raise both sides to the 1 over 0.3, the reciprocal, to get just L on the left-hand side, equals 3.32 to the 1 over 0.3 power. 1 over 0.3 is 3.33333. And so L is going to equal 54.6, which is in the neighborhood of what it looks like on our graph over here, a little less than 55. How many units of capital are we going to use? It's kind of a trick question, but it's one that you need to be able to answer, right? We have 20 machines, so that's what we're going to use. And now we want to figure out the total cost. So remember that labor costs $10 each. Machines cost $20 each. If we add up our total costs, we're going to end up with 20 times 20 for capital, which is $400 for our capital bill, plus $546 for our labor bill. And again, especially since this is the short run, it makes a lot of sense to call this $400 fixed costs and the labor costs variable costs here. So our total costs for making 1,000 units would be $946. If we divide that by 1,000, then our average total cost, or our cost per unit, is going to be about 94 or 95 cents each. So it's a little simpler to solve this because there's only one variable. We know K is 20. We just solve for how much labor we need to figure out how we can produce 1,000 units. One other thing we'll do in cases like this is, since there's only one variable, it makes this idea of making a function to figure out how many workers we need today to produce a certain level of output a little easier than what we were doing when we had two variables up above. In this case, what if we just left Q a variable, but we did everything else the same that we were doing over here on the right-hand side? Do you think you could see how to solve this for L? So a labor requirement function is just when you solve for L as a function of Q, that lets you plug in any quantity and then tell you how many laborers you need to achieve a certain level of output. So if we were to start right around this point, I think you can see how we could do that. So instead of having Q equals 1,000, we would just have Q over 50, right? Q over 50 equals, and then we'd have L to the 0.3, 20 to the 0.6. So then we'd need to divide both sides by 20 to the 0.6, right? And what we'd end up with here on the left-hand side is Q over 301.71 equals L to the 0.3. And then we'd need to raise both sides to the 1 over 0.3 power. And so we know we're going to have Q to the 1 over 0.3, which is 3.33333. And then in the denominator, we're going to have 301.71 raised to the 3.33333, which is going to give us about 184,200,477.2. And again, there's some rounding error in what we're doing here. And then that's going to equal L. So if we plug in 1,000 for Q in this function, it should give us the same 54.6 here for the number of workers we need, and of course we're still going to have 20 machines. The last thing I want to do in this problem is answer this final question here. If you were in this situation and you had a factory with 20 machines, what would you want to change in the long run? And what I'm thinking here is, let's compare this result, where to produce 1,000 units today, given that we have 20 machines, is costing us $946 to produce. 94 or 95 cents per unit. Let's compare that to the long run optimum. And we found in the long run what we should be using to minimize our costs of producing 1,000 units is more machines and less labor. 28 machines and less labor than we're using here. Less than the 54 or 55 workers. The whole point here is, suppose you were operating a factory, you knew you were going to be producing 1,000 units every day, then what should you start doing in long-run planning? If you only had 20 machines, you should start trying to make some plans to get some more machines in your factory, use fewer workers, and then you could lower your costs in the long run. So as always, if you have any questions, please let me know. Otherwise, this is Dr. Berkey signing out, and I wish you the best of luck. Talk to you later, guys.